Okay.
Okay, before we resume, let me say that we are going to have a gathering after the last talk. We're going to have dinner at the restaurant Tradição Imperial at 7 p.m. It is in Rua General Dionísio 11 in Humaitá. We are going to be leaving, many of us are going to be leaving from here. So I just want to make sort of to have an idea, an estimate of the number of people. So if you are planning to come, can you please raise your hands? Okay. So now I pass the word to Olivier.
Hello, everybody. So our next speaker today is our new colleague, Sokratis Zikas. So he comes to us from Poitiers, where he was a postdoc of Enrique Flores, and he did his PhD with Jérémy Blanc in Basel. And he'll give us an introduction to the Sarkisov program.
Well, thanks for having me, first of all. I must confess that I thought this was going to be more of an informal meeting, so I may be a bit underprepared. Feel free to fill me in with questions and things like that. All right, so the idea of this talk is to not talk too much about like math, but give some ideas and about like the overarching like background of my research, which is which is the Sarkisov program. So, well, my topic is birational geometry, so we're interested in birational maps. And the main object of interest is a group BRX, so we fix a variety X. And we look at a group of birational maps from X to X. And let me say that the more interesting case is, well, the simplest the X is, the more interesting. So if you take a general variety, BRX is a finite group. There's not much to say about it. So we're interested in X. We want it to be as symmetric as possible. And from the point of view of higher dimensional birational geometry and MMP, this means that X is what we call a Mori fiber space. I'm not going to define it, but it's there are varieties with simple structure, and the prime example is the projective space. So the main tool to study this group of birational automorphisms until now has been the Sarkisov program. So what does it say? So the Sarkisov program says that if you take so if F is a birational map between Mori fiber spaces, then we can decompose it. We can decompose F in simpler maps. Which we call Sarkisov links. Again, I'm not defining anything. I'm not defining what Sarkisov links are, what Mori fiber spaces are, but just you kind of have to believe me that they're simpler. Why they are simple? So some of the main features. So first of all, they are much easier to construct. They're very easy to construct. And once you construct them, they have a very simple structure, so it's very easy to say they have a very easy structure from a birational point of view. In the sense that you can say, it's easy to say what curves are contracted, what varieties are extracted, what are the exceptional divisors of the map and its inverse, and so on. And well, I say that they're very easy to construct, but this is only if they exist. So it's also it's sometimes easy to say when they exist. Well, so while the first version of the Sarkisov program was proved in 1995 by Corti, you could see traces of it from before that. So the first trace of it was one of the ways that it has been utilized. So main ways it was utilized. So I say that sometimes it's easy to say when they exist or not, So one way to utilize it's the following: prove that there are no Sarkisov links. That there are no Sarkisov links starting from a variety X. Well, since Sarkisov links decompose any birational map, this means that there is no, non-trivial birational maps from a variety X. And this is what we call, so this means that the variety is called super rigid. In particular, if there is no birational maps from X to anything else, then, for example, X is not rational. It cannot be birational to projective space. And this is what Skovsky and Manning used to prove that the quartic threefold is non-rational. So smooth quartic threefolds are not rational. Well, another way that it has been utilized classically is to, since they're easy to construct and to control their structure, you can construct increasingly more and more complicated links. So.
You said that Corti proved it in 95.
Yes, yeah. No, I don't know.
These results are from the 80s, right?
Yes, I think these results come even before Sarkisov work on conic bundles. I think back then it was, they basically developed what they called for many years the method of maximal singularities. And then after that, there were some results of Sarkisov, and then Corti proved the first version of it. Corti's work? Sarkisov, yeah. Okay. Well, I'm not so sure on the exact timings, yeah. Okay, another way is to construct increasingly complicated links. And somehow this should reflect it should reflect the complexity of Px. So for example, in many cases, if you take modifiable spaces that have conic bundle structure, and you construct Sarkisov links from the conic bundle to itself, and then you ask that the they are more and more complicated, and these somehow sometimes define infinite filtrations on your variety, and so that it's, infinite filtrations on the group Prex, and then it shows that it's very, very complicated. So basically this is the only two ways the Sarkisov program was utilized for many years. And then we have, well, let's say the modern version of the Sarkisov program. Which is due to Hakon and McKernan. So let me say that the proof of the Sarkisov program for dimension 3 was first done by Korte in 95 in dimension 3, and it involved like studying very complicated invariants of the map, and then you start with a map from X to X, or from X to another variety Y, and then you attach to it some invariants, and then you ask that you perform one Sarkisov link so that you decrease these invariants, and then you ask that you prove that there is this invariant satisfy some descending chain condition, and so at some point you have to decompose your map. But this approach only works in dimension 3. It's very complicated. But then we have this modern interpretation of the Sarkisov program, which works in any dimension. And the idea, very, very rough idea, is the following. So we start with a birational map from X to a variety Y, and then we resolve this map. And so what Hakon and McKernan do, they use some techniques from the MMP and finite generation of the canonical ring, and then they go on W, and they go on the space of divisors of W up to numerical equivalence, and this is a vector space. And then up there they define some polytope. They define some polytope there where, well, everything works as best as we could hope for. So that kind of works as a Mori dream space. We'll try to make this slightly more precise in the next step. So then what they do is they take a two-dimensional slice. So take, or W, sorry, you're right, thank you. Yeah. So now you take a two-dimensional slice. A general one at least. And then what you see is, well, you see a polytope in dimension 2. And then what I meant that this works as best as it could as a Mori dream space, I mean that, well, this polytope has a wall and chamber decomposition. So this polytope corresponds to divisors that you can basically run MMPs, and everything works and everything terminates and everything is very nice. And then you can now on this polytope take a wall and chamber decomposition based on what are the outcomes of these MMPs. So if two divisors give you the same output, then you put them in the same chamber. And then what they prove is that you have a wall and chamber decomposition, something like that. And then, of course, you can realize X and Y as certain MMPs on W, and they prove that actually the points that correspond to X and W, they lie on the boundary. And then they show that, well, a Sarkisov program that decomposes this map is actually a walk around this boundary. So you just walk, you just choose one way to walk. And then every time you see at least two chambers meeting on a point, this corresponds to a Sarkisov link. So in my picture, this map would have a decomposition into two Sarkisov links in this very simple picture. This has like some. Yeah, this is what. By the way, this is what this idea was proposed by Sokurov, and he called it the geography of ample models. So it has good things and bad things. One of the bad things is that it's not effective at all. It's not explicit at all. So before that, in the proof of dimension 3, I give you a birational map. Well, it gives me decomposition to Sarkisov links. It's sort of an algorithm. Here it's just very abstract. Take your resolution, define this polytope, then you can cut it with many, many, many different two-dimensional slices, two-dimensional subspaces, and then each one of them might give you will give you a decomposition. There's many of them, nothing too explicit. On the other hand, again, even after this proof, there weren't many more applications of the Sarkisov program. But then came Blank, Lamy, and Zimmermann. That basically used the same idea, and they said, okay, what happens if we don't take two-dimensional slices? What happens if we take three-dimensional slices, or four-dimensional slices, and so on? And the idea is that these things should somehow encode the relations between Sarkisov links. So so relations. So they said that relations between Sarkisov links correspond to higher dimensional slices. And they developed this theory of rank R fibrations. So the R is the dimension of the slice of the polytope that you take. So again, I said that Sarkisov links, they decompose birational maps, but the main problem with Sarkisov links is that even if you start from a birational map from X to X, the Sarkisov links don't have to be from X to X. It could be, you could go to some other variety, Z, and then from Z you go to another variety, and in the end of the decomposition you're going to end up back in X, but each Sarkisov link is going to be to a different variety. So in a way what this says is that this generates something, the Sarkisov links generate something, but they don't actually generate the group Brex, they generate a groupoid. So one can define the groupoid Bir-Mori, which is, well, birational maps between varieties birational so Bir-Mori X. And then what the Sarkisov program says is that this groupoid is generated by Sarkisov links. Well, and then what Blank, Lamy, and Zimmermann did is they found the relation. So now we have a presentation for this groupoid. So we have some presentation. So this is Sarkisov links. And, well, they say that you don't have to take all the relations. You only have to take the ones that correspond to three-dimensional slices. These are enough to generate the relations. So rank, I'm going to write rank 3 fibrations. But yeah, you should think of just take your polytope and cut it with three-dimensional slices and see, well, there's many ways to go from X to Y, and, well, you can go around. It kind of will look like a ball, and you could just go around different paths, and that would give you different decompositions, and the corresponding links will have, there will be some relations controlling them. All right, so one of the many ways that that now this has more applications than the previous interpretation of the Sarkisov program is that, well, if you have a presentation for a groupoid, you can write homomorphisms from that groupoid. So one can write homomorphisms So, well, you just have to, if you want to write a homomorphism, you just have to just say where your generators go and then check that your relations are satisfied. Well, in the end, we want to study Brex, but we ended up with a groupoid, Birmori-X. But what happens in many, many cases is that you can define a groupoid homomorphism to a group and then restrict that your group Brex lives in Birmori, right? So you can write homomorphisms and then restrict them to Brex, and then you get homomorphisms from Brex to different varieties and to different groups. And then in the end, what they managed to prove, for example, was that, so they proved, one of their applications was that, well, the Cremona group is not simple. They managed to write down a group homomorphism from Birmori Pn and then restrict it to the Cremona group and so that it's a non-trivial homomorphism. So it has some kernel, and then we have normal subgroups. And this was an open problem for many, many years. And after that, there were many more applications. You can make more explicit constructions. Sometimes you might be able to endow this with well, direct product structures if you can control the relations very well. Later, they managed to write a homomorphism to Z, for example, which was not easy in the beginning, and then you get extra results, and so on and so forth. All right, okay. So this is the state of the art, let's say, of the Sarkisov program and the theory of rank R fibrations. So, yeah, a lot of my work is based on that. But what I want to say is that there is many ways to somehow improve that. One can try to, let's see. So what you need here is here, the way that they obtain these polytopes is through various MMPs. And so technically, like heuristically speaking, any property that can be carried through MMP should be able to be reflected here. And at the same time, any property that you might be able to see on this space and preserves your polytope, it should be able to be reflected here as well. So for example, people have proved the Sarkisov program like that for where you also have the action of a connected group. You can see the group acting here, and then you can show that it preserves the polytope and that with every MMP it descends. So you can do Sarkisov program with connected groups. You could try to do some version with finite groups as well, and many other ways. Any property that you can see in an MMP, you could also probably see it here. So for example, there is this variant of the Sarkisov program, the volume preserving Sarkisov program, which the proof is more akin to the old proof. But if one could reinterpret it in this framework, then maybe one could also say something about the relations in that case. Or another one of, another thing that I was thinking of exploring is the following. Let's. No, it's not. But the proof does. I think the proof doesn't look like that, if I'm not mistaken. I think it's more. I think it is available, right? Yeah. I'm not an expert in that. I think it is available, but I think the way that they prove it, it's not like that. So it's not very easy to replicate the second step. But I think that with some work, if one can show that you can do everything in a volume-preserving way, you could get this version. Another thing that one could try is the following. Let's say that you go that your birational map goes from X to X, and you can regularize it on W. Then you're going to have an action of this birational, the group that is generated by this birational map here. And then what can you say? How symmetric can this be? For example, let's say that you start with an involution from X to X, and then you regularize it on W. Then your involution is going to act on this polytope. So this polytope is going to be if you take also a nice two-dimensional slice, your polytope should be symmetric in a way. What can you say about, what does the symmetry give you about the original map? For example, if you can find a two-dimensional slice such that the involution acts by reflections, for example, along a line, then this would tell you that the Sarkisov decomposition is symmetric. So actually your map is a conjugate to a Sarkisov link that is an involution. And that should give you some information. Or then the question is, what happens if you can never find a plane like that? What if for every plane it's a rotational symmetry? Could that give you some information? I think these are all things that can be asked. And yeah, I think there's many things to explore here. That's what I was trying to say. Well, I guess that's all I wanted to say.